Okay, welcome everyone. This is a session on the Event Horizon Telescope. It's a visionary project to take the first photograph of a black hole. We are a collaboration of over 200 people internationally, and there are 4 of us here to walk you through some of the aspects of the entire project. I'm Shep Dolman, and I'll be talking about seeing the unseeable, building an Earth-sized telescope. In 1919, there were 2 expeditions set out by boat, one for Sobral off the coast of Brazil, and one to Principe off the western coast of Africa. And they were aimed at doing one thing, observing the 1919 solar eclipse to test whether Einstein's theory, which had been born just 4 years earlier, was correct. Einstein thought, and he calculated, that the light coming from stars near the limb of the sun would be bent by a precise amount, and Newton had a different prediction. And when the 2 expeditions came back and developed their film, they found the following. The positions of the stars, shown here with these lines, had did by exactly Einstein's amount. And overnight, he became a household name, and our concept of gravity changed from this force at a distance concept of Newton to this idea of geometric bending of space-time of Einstein. It was quite remarkable. It changed the way we looked at the universe. Now, I would have given anything to have been on one of these ships. And that's saying something because I famously get very sick at sea. But the reason is I'm an observational astronomer, and I love this stuff. Everyone in the Event Horizon Telescope does. And the Event Horizon Telescope is dedicated to the proposition that we can do this again, but not around the sun, but around a black hole. I think we all know that the idea of a black hole is that you get enough matter into a small enough volume that the force of gravity is enough to restrain light from escaping. So if we could make the first image of a black hole, see light bending around it, we'd be able to test Einstein in the most extreme environment that we know of in the universe. So the best case we have for doing this is the supermassive black hole in the center of our Milky Way galaxy. And we'll take a short trip there. First, you pass some known constellations, and you go through gas and dust, and pretty soon you're going so deep into the galaxy that only infrared light, X-ray light, and radio light can penetrate this. And you finally get to a place where you see radio light of streamers of gas feeding a central supermassive black hole that's shown here in the white dot. We think that is a 4 million solar mass black hole. Now, how do we know that? Because the infrared cameras have captured the motions of stars orbiting around this black hole. That's what you see here. Nowhere else in the universe will you see stars being tossed around like planets. It's really something. And what we want to do with the Event Horizon Telescope is zoom in by another factor of 1,000 to see what's in that central region. Now, theorists told us some time ago what we might see. This is a ghostly image from 1979 made by Jean-Pierre Luminet of what an accretion flow, a pancake of orbiting matter might look like when lensed in the gravity of a black hole. And you see this shadow feature, that dark patch in the middle. Einstein told us 100 years ago exactly what the size and the shape of that shadow should be. If we could lay a ruler across that shadow, we'd be able to test Einstein's theory at the black hole boundary. The problem, though, is that this feature is so small that it's the equivalent of seeing an orange on the moon, or being able to read the newspaper in Los Angeles while you're sitting in New York City. So we need to think about a new kind of telescope. How can we make this image? Well, a normal telescope, a radio dish, that you probably have some idea of how it works, is simply not up to the task. The parabolic shape of this dish reflects a plane wave of light so that every bit of the light reaches the focus at exactly the same time. So organically and geometrically, all the light is combined. But the magnifying power of this dish is limited by its size. And if we want to image the shadow of the black hole with radio waves, we would need a telescope as large as the Earth. So we can do this by using something called VLBI, Very Long Baseline Interferometry. That's basically a word salad for taking a ball peen hammer and smashing that original dish and spreading the fragments of the reflective surface all over the Earth. In reality, we do it by linking up radio telescopes on different continents, and we time the data taking perfectly with an atomic clock that loses only 1 second every 10 million years. And we record it on custom-built high-speed data capture systems with digital signal processing that can handle the torrent of data. And we bring that all back to a central location, and we play it back with precise justification so that we recreate this parabolic dish but on an Earth-sized scale. We do in silicon what a radio dish does with its shape. And when we do that, we get the resolving power or magnifying power of a dish as big as the distance between those two radio telescopes. But with only a few dishes around the globe, it's almost like having little bits of silver mirror. You haven't filled in that mirror. How can we do that? Well, the answer is right under your feet. During a night of observing, the Earth rotates. And every baseline pair, every pair of telescopes gives us a little bit of information. And we fill in, you can see on the right, that virtual mirror. So all the connections you see in purple there give us one more bit of data. And after a 6, 7, or 8 hour observation, we filled in enough so that we can make a high fidelity image of the black hole. Now, with these instruments, we're taking all these systems on a global roadshow. We've started with the first 3 sites here in the continental United States and Hawaii, and we've expanded to the Large Millimeter Telescope in Mexico, and also now in the ALMA array in Chile. Okay, we're working on it. We actually do this much better in real time when we actually do the observations. Our European counterparts and colleagues have brought 2 telescopes in France and Spain. And then we have the South Pole Telescope, and also we've added the Greenland Telescope at the other end of the Earth. And this is not really getting on a boat, going to Sobral, or going to Principe, but we go to some pretty extreme places ourselves. So here's a picture of some of the team from the University of Arizona retrofitting the 10-meter dish at the South Pole. It gets to be minus 40, minus 50 degrees, and that's when it's warm. And they're retrofitting this dish for a purpose that it was not intended for. So we're getting a new kind of telescope using existing radio telescopes. Here's the Greenland Telescope. It's also very cold there, and the spice here is that polar bears occasionally walk through the camp. So it keeps some of the team there on their toes. And then here's one of my favorites, the Atacama Large Millimeter Array in Chile, where you need bottled oxygen, really to keep your head straight. Otherwise, you suffer from what we call summit moments. So what I wanted to explain is that with the Event Horizon Telescope, we're setting about doing something very, very new. And in April 2017, we took our first data. That was almost 2 years ago. So why don't we have an image yet? The answer is that we're analyzing the data now. And in some ways, if you are going to come with a big claim of imaging a black hole, you have to have big evidence, very strong evidence. And in our project, we often think that people like Einstein, Eddington, Schwarzschild are kind of looking over our shoulders. And when you have luminaries kind of virtually checking your work, you really want to get it right. And we hope to come with results this year from these first observations. Now, this global project requires a global team. And we have 200 people around the globe helping us. And there are 4 of us here today to talk about the project. I'm the project director, and I've been working on this for about 20 years. It's been the work of a career. And we have Dimitrios Psaltis, the project scientist, who's an expert in general relativity, who's going to tell us more about what we might see. We have Sarah Markov, who is an expert in modeling black holes, and she's going to tell us about the impact of black holes on the universe. And then Peter Gallison is a renowned expert in history and in philosophy, and he's going to walk us through what it would mean for us as humans to make the first image of a black hole. Now, Dimitrios.
Everybody can hear me? Excellent. Thank you, Seb, for the wonderful introduction. And as Seb said, the Event Horizon Telescope has 2 main goals. One is to take the first ever picture of a black hole in the universe. And the second is to ask the question, was Einstein 100% right? In other words, since we have this theory for more than a century now that tells us how black holes behave and look like, if we make predictions with that theory and compare to the observations, do we get the same answer or not? To reach our first goal, we built this enormous worldwide telescope. To reach the second goal requires different technological innovations that I would like to guide you through. And this is something that we couldn't do even 5 years ago. And let's start easy. Of course, I'm going to be talking about general relativity, and a lot of you are thinking about a lot of math, which is exactly what it is, but I'm going to show you no math whatsoever. I'm going to show you some animations. And a black hole is nothing but an extreme warp in space-time, so strong that does not even let light escape. So nothing simpler to see than to explore, visualize what light does in the presence of a black hole. And to start easy, this is my depiction of space-time, a flat sheet of paper. I'm going to throw photon torpedoes now. These are those red lights. And when there's no black hole there, light does nothing but move if it starts. Light does nothing but move forward without being deflected. But now what I'll do is I'm going to throw a black hole in the middle. It's going to warp space-time. And when I throw those photon torpedoes now, they start deflecting light. This is what we call gravitational lensing. But perhaps more importantly, all the light that goes into the black hole never escapes. This is the definition of a black hole. So if I'm going on this side and look backwards toward the black hole, what I will see is that the black hole will cast a shadow, will cast a silhouette, like the ghostly picture that Seb showed before on the surrounding emission. And this is what we're after. We want to take a picture of a bright emission in the center of the galaxy and look for that circular black, really black silhouette that the black hole will cast on it. Now, doing those calculations, as I said, requires a lot of computational power because these are very complex equations. And even 5-6 years ago, we could only do them using supercomputers. But then what we realized is that each one of our laptops, actually each one of your cell phones, has specialized hardware that does this kind of calculation. They're called GPUs, the graphics processing units, and all your computer gaming use it in order to render those nice three-dimensional pictures that you see when you walk through a room, to play your game virtually. So what we did is we actually hacked those GPUs and made them do the calculation in the presence of a black hole. And that changed the game completely, because now we don't need supercomputers. We can do the simulations on our laptops. And even more fun, they're so fast that we cannot type fast enough to control it. And instead, we're using another technology from computer gaming. We're using our hands. This is a little demonstration of it. This is the Leap Motion Pad. Our colleague from the University of Arizona is running his simulation. He's saying hi to the Leap Motion Pad. And he's going to use his hands to drive the simulation forward. This is a real-time simulation of solving complex equations in general relativity with 1 million light rays thrown to the black hole. He's moving it forward, he's moving it backwards in time, and at some point you see, now we zoomed in, you're going to see that the black hole casts this nice circular shadow that I was talking to you about. You might ask yourself, why are we doing this? This is the shadow. Well, it is the same thing that you do if you're a pilot and you're getting in a flight simulator, right? You try to see how you will react, how you will interpret what nature throws at you in many different conditions, so that when you get in the right, in reality, and you get in a particular situation, you know how to react. That's what we're trying to do here as well. We're asking ourselves, what if black holes behave like this? What if the plasma around it behaves like the other way? If we look at this direction or the other direction? We improve our intuition, so when we look at the data that nature throws at us, we know how to interpret it and what to do with that. So this is what we did to make things fun and fast, but then we became greedy. And we said, okay, if we can do those simulations on the laptop, what if we make a supercomputer of these GPUs, which we did. And now we don't just throw photons onto a black hole. We throw plasma, and we throw gas, and we throw magnetic fields, and we do a weather forecast, just like what your weather forecast does. We make the most realistic possible simulations of what black holes look, given our current understanding of physics. But then we got into a different problem, because now we're generating hundreds of gigabytes of three-dimensional volume data that we don't know how to explore, right? It's not just enough to show them on the screen anymore. But thankfully, technology these days evolves as fast as our appetite. So what we do is we started using augmented reality to explore the virtual worlds that we make. This is an actual picture. These are two of our PhD students. One is, Leah Medeiros is actually defending her dissertation in this Tuesday at the University of Santa Barbara. And one of them is exploring the three-dimensional volume of what happens close to the black hole. The other is exploring in the same time what happens, what an observer would look at the telescope will look like, and they figure out what structure near the black hole gives rise to a particular feature in the image. These are the kind of things that we do to simulate and predict what if Einstein is right, what would the black hole look like. So now we have all the ingredients, we throw them together, and we can make a beautiful simulation of what the black hole would look like. And this is not what we expect to see, because what I first did is that I tweaked the wavelength of observations, not where the placed in electromagnetic spectrum not when the event horizon, where the event horizon telescope observes, which is at 1 millimeter, but I made the wavelength a factor of 10 larger, a centimeter, half an inch. And if we were to observe there, as we've done before, you would see a big fog, that plasma surrounding the black hole. But as I crank up the energy of the photons, reduce the wavelengths, just like the X-rays, as you use X-rays as opposed to optical light, you can penetrate through your flesh and you see your bone, then what we can do is we can see what happens when we go to the wavelength of the Event Horizon Telescope. The fog becomes transparent, and we get to see that elusive shadow. And not only that, but because we can do the full weather forecast, we can do the time-dependent, mesmerizing simulation of what the black hole shadow would look like. These are kinds of simulations that, as I said, a decade ago were not possible, but now they're done in many groups in the collaboration all over the world, in Asia, in Europe, in North America, and other places. And even though the things, unfortunately, you cannot see it very well, things around it are very variable and turbulent, what is constant inside is that beautiful shadow, which has a size and a shape that we can predict to exquisite accuracy. And this is how we ask this question. When we look at the data, when we look at the actual image that our observer friends are going to show us, the question is, does it have the size and the shape, that we can actually predict now? If the answer is yes, then Einstein was 100% right. If the answer is no, then we have to tweak his theory in order to make it work with experiments. This is how science goes. So what I've done so far is that I zoomed all the way into the black hole to show you what we expect to see for things that happen very close to the horizon of a black hole. But what you'll hear now is that those little black holes affect the universe and the galaxies in which they're surrounding. And this is part of the story that Sarah Markov will continue. Thank you.
Okay, so hi everyone. Now that you've heard a bit about why we're interested in building this, I want to talk more about why resolving this region very close to the event horizon is actually so important for understanding astrophysics, cosmology, and the role of black holes in the universe, and I'm going to give you a sense of some of their impact. Now, before I do that, I have to give you a feel for the size scales in the universe, which isn't really something that I think many of you think about on a normal basis. So let's take a step back, if this moves, okay, to think about the home of a supermassive black hole, which is a galaxy. Now, Shep, I think, mentioned that every galaxy we know of, we think has a supermassive black hole in the center. And so if we could zip out of our own galaxy, we'd look in, we would see something like this. The supermassive black holes that we look at are incredibly huge. I mean, basically, one of the EHT targets is about 10% of the size of our solar system. Okay, so this sounds a bit crazy, a black hole that big, but on the scale of the galaxy, that's just nothing. All of these billions of stars in the galaxy are solar systems. And so a supermassive black hole on that scale is really trivially small. And this black hole in the center of our galaxy is basically, wow. Our galaxy is 50 billion times bigger than the black hole. So really, it doesn't actually feel the black hole at all. And the black hole, you could replace it with a rock as far as it's concerned, and it really wouldn't matter except very close in. But that's only true because we have what's called a dormant black hole in our galaxy. And there are many other types of black holes, and occasionally they become what's called active. And when this happens, gravitational energy is basically, the black hole is basically capturing material, and it's managing to convert this into other forms of energy with an efficiency that's basically 100 times better than the next best thing we know of in the universe, which is nuclear fusion, which is forming stars, powering stars, and which we could capture here on Earth, actually. And so the thing is, to understand that kind of activity, we actually can't see this with our own eyes. We need to build telescopes that go from the entire electromagnetic spectrum, from the radio up to the gamma rays, to show us what we can see. And so what I'm going to show you is another type of galaxy. Now, it doesn't look like much. This is what our eyes would see if we had really good eyes, like the Hubble telescope, which took this image. And you see a ball of stars. It's an elliptical galaxy. But now, if we look at this system, and it's in this active state with radio waves, we're going to see something quite different. Radio waves trace magnetic fields. So now, on the exact same scale, you're going to see something else. Now, you can't see radio waves with your eyes, so we convert this to blue so you can see it. But I'll go back and just show same scale. And that tells us that this supermassive black hole is shooting out enormous fountains of magnetic material out to about 100 million times the size of the event horizon itself, pretty much at the speed of light. And these particular systems are actually 800,000 light years across. So that allows us to actually do some kind of extragalactic archaeology, we call it, because the plasma that's out at the ends here means it left the black hole almost 1 million years ago. And we can also see blips of activity that tells us about maybe every few 100,000 years the black hole is going through cycles. And so this is something we really would like to understand, and I'll show you a little bit more about that. But we can also look at other wavelengths, and the X-ray is probing the hottest gas in the universe, and basically our solar corona is emitting X-rays. So we're talking about gas that's 10 million degrees Fahrenheit or so. Now, space is about minus 450 degrees Fahrenheit, so this is extremely hot. And if we switch now, same size scale, it's a little hard to see on the screen, but there's an enormous ball of very hot gas surrounding this entire system. So we think actually a lot of that energy is being injected not only by the black hole, but by the formation of the black hole, which I'll talk about next. And so putting this all together, we see a very complicated system that's being driven by this black hole, and it has basically wreaking havoc on its environment. And for instance, we can figure out how much energy is being put into the system also by calibrating the holes that these jets are carving out. They have to push gas away. And sort of like blowing a balloon, you have to do work to inflate a balloon. We can figure out that the energy of about 10 billion supernova has to be put in by a single black hole into making these big cavities. And also, they're about 600,000 light years across, so just dropping our galaxy in, it gives you some sense of how incredibly large these structures are. This is very mainstream. This happens all the time. Now, one of the things that I didn't mention in this is that all of these white spots here, they're not stars. Those are other galaxies. So what happens is galaxies get grouped together, held together by gravity, and they're basically the largest bound structures that we know of in the universe. And these galaxies are moving around and they're merging with each other, and they form bigger galaxies and bigger black holes. And we think that the black holes, via this type of feedback, are actually helping regulate this. Also, stars don't like to form in hot gas. They basically need the coldness of space. So for galaxies to grow, even just in this environment, you need to, you basically have trouble, and the black hole can regulate the growth of the galaxies in this big halo. So we see pictures all the time. This is a beautiful image of two galaxies colliding. So we caught it in the act. And eventually they're going to come together and merge and form this mega black hole in the center of a big galaxy. And we think that the black hole becomes activated also during this time. And I'll show you a movie of a simulation of the end of stage of two galaxies merging. And basically you'll start to see that these black holes in the center become active and start to basically blow apart everything. And by the time the two black holes come together to merge, they've just created complete havoc in the system. Now, millions of years later, this will condense into what we think of as a normal galaxy with a bigger black hole. But we now know that the black hole has a regulating effect and basically limits the size of what this galaxy will actually be in the center. So this gives you some sense of the cosmic importance of black holes, and they're really one of the only things we know of that can affect the structure of the universe at the largest scales. But coming back to Earth a little bit, when we want to try to connect what we're seeing near the event horizon to these incredibly large scales that I was talking about, we need to combine our observations with the Event Horizon Telescope probing the event horizon to these scales that we see with other frequencies. And so we combine our observations with global facilities on the ground and also facilities from space. And ultimately, what we try to do then is we see these types of structures all over. Like I said, there's billions of galaxies, and each one has a supermassive black hole, and we try to calibrate the role of the black hole. And so we're trying to connect, effectively, microphysical processes that are happening right at the event horizon, somehow combine, create magnetic fields, and launch these enormous structures that are far bigger than the galaxy that hosts it itself, and we don't understand this process fully. So as Dimitrios was saying, we build computer simulations, often using GPUs these days to accelerate them. And for instance, this is a donut of material that's being wrapped around a black hole, and we let it go. And what happens is we can actually, from first principles, model the effects of the magnetic fields, channeling down at the scales of the black hole, all the way out to physical scales, and try to look at these massive structures and compare this to the data that we get from EHT and with multi-wavelength. And hopefully from this we can, our idea is that EHT is the anchor, and it's revealing the roots of these cosmic structures, and we can try to tie this together and make a more complete model. So we're going to move on now to our last talk from Peter Galison. I've sort of given you a sense of the importance of black holes in the universe, and now he's going to talk about the importance of making images of black holes for people.
This project, as the colleagues have mentioned, has been going on for years and years. It's a complicated theoretical problem, it's an instrument problem, and it's an image-making problem. How do you make an image that's 1,000 times more fine-grained than what we've seen before? What I'm thinking about the history of image-making in science, which has radically transformed science over many centuries, we come really through several different stages. Each of them builds on the other. Each of them teaches us something new about what an image can do. In the 18th century, I'm schematizing horribly, but in a cartoon version from 1730, say, to 1830, you have a kind of metaphysical notion of what an image is. For someone like Goethe, who studied clouds and plants and insects, who contributed hugely to many branches of science, you had to get behind the curtain of ordinary experience. He didn't want to know what this cloud was like now or that moth-eaten plant outside the window. He wanted to know what the perfect version of it was, the ideal behind any particular. In the next century, beginning in about 1830, people began to talk about another kind of image, what they called objectivity, or an objective image, for the first time in a form recognizable now from the present. And the idea of mechanical objectivity was to find a way for nature to write itself or draw itself or imprint itself on the page by tracing it or eventually by using photography, many different techniques to try to get nature onto the page with a minimum of interference by us. So if the first stage, the stage of finding a metaphysical picture behind any particulars, required a kind of sage or genius, the second one required very great self-restraint to allow nature to speak or to draw without us. In the 20th century, people began to recognize that just taking the image straight up from nature to the page could be highly problematic, that we needed to use our trained expertise, not because we're geniuses, but because we learn how our apparatus works. We learn to know when the apparatus is giving an artifact, when it's deceiving us in some way. And only the combination of instrument methods and trained expertise can get us the kind of image we want. We're now at a moment where all of these have, in many ways, combined in this attempt to make an image of the black hole. We try to look at what would be an image that would synthesize other images. We try to look at images that are produced as algorithmically as possible so we can assure ourselves that we didn't impose our ideas on the reality, that the image is really out there. And we used our trained judgment to address some of these images. All of these get combined and are focused like a laser on trying to make this image that will be the product of this effort if it's successful in the coming period. Now, why make an image of a black hole in particular? And why do we believe that black holes exist experimentally or observationally? Well, the first really strong observational arguments or evidence for a black hole came back in the early 1970s when a star, a visible star, was seen to be orbiting around an unseen partner. And some of the junk from that, some of the gas and outflow from the visible star, started swirling around this other unknown thing. And you could use the properties of the X-ray pulses that arrived at Earth to tell us that it was very small. And you knew from the motion of the big star, of the visible star, that how much mass it should have. And so some people said, this is a good argument for being a black hole, a stellar-sized black hole. But many people were not persuaded. And many of my illustrious senior colleagues then said, it's interesting, but it's not yet proof that we have a black hole. Then the kind of the kind of observations came up that, that Shep showed earlier, where you see a star being whipped around the center of the galaxy, of our galaxy, of the Milky Way galaxy, and you can use that at a much bigger scale to understand the kind of thing that X-ray pulses told us about in the 70s. Now you can see that a hugely massive object, millions of times the mass of the sun, is dragging whole stars around it, and that became one of the yet another form of evidence for black holes. Of course, LIGO, the great success of gravity wave detection that took place starting in 2015, began to give us a sense of what happened close in. If the observation of the star being pulled around the center of the galaxy gave us images, but 1,000 times farther than the horizon of the black hole, LIGO told us something else. It told us up close, but without an image. The image that's on the right here is a simulation. What we actually get are these pulses measured at different observing stations. So what would it mean to have an image of a black hole? Why do we crave, why do we long for an image of things we're trying to demonstrate in science? Let's go back and, as Sarah did, to expand our scope, look wide, only this time in history. If you look at the 17th century, when Robert Hooke used a microscope to draw some of the things he was seeing for the first time in the subvisible world and drew this detailed picture of a flea in 1664, it opened a world. It was terrifying, amazing, astonishing to people at the time because it allowed them to be able to articulate what happened below the threshold of the very small. When in 1892, Röntgen began to turn his X-rays on the human body, on even the living human body, and we could look inside the functioning of our own physiology for the first time, that was also kind of horror, but fascinating, but profoundly important for an understanding of the way the body worked. In 1969, with the Earthrise picture that took the whole of the space program, a decade and longer if you think of it as starting with the whole beginning of rocketry, gave us a picture of the Earth from somewhere else. And this was something that had an astonishing, sublime effect in a way. Sublime in the sense of giving a kind of dignity and broadness to vision that was something beyond what we could have, to see ourselves seen from afar. What the black hole image could do for us, if we can get it, would be to take something that is the most extreme, the strangest prediction of general relativity, one of the great accomplishments of the human mind, to combine it with the most advanced electronics, with a planetary scale collaboration, with the most advanced statistics, with new imaging techniques. It's like making a new camera with a new kind of film, a new kind of lens, combining it with other cameras all at once. And if that could happen, if we could actually get in and see right up close to the horizon, it might demonstrate to us that black holes exist beyond the shadow of doubt. Thank you. May I invite the colleagues back to the podium here, and we will have a chance for you to ask questions, for us to discuss any aspect of this that interests you.
There's one point I forgot to mention. We have Google Cardboard devices. People will have them over there. At the end, you can have a look, get one for yourself, and you can join us in a virtual tour of all the telescopes around the world.
So if there are questions, we have some people who have microphones, right? The runners? No. Yes. Ah, there's a microphone being set up there. Please come forward if you have a question.
Everybody's more interested in the boxes.
That's the question.
I should have said that at the end.
Everyone wants the virtual reality.
Yeah, not the reality.
It's not, I don't think it's on. Oh, it's on! Oh, sorry. I had a question about some of your initial findings that you haven't released so far, just if there's anything that you feel might reshape our idea of space-time, not just, I guess, as we understand it around the event horizon, but also how that might affect us as just normal people.
Demetrios, would you like to take a crack at that?
I definitely can. I think the main question here is, let's say that we do find that Einstein was right or Einstein needs to be tweaked. What does that affect what we do in everyday life, right? Yeah. And the answer here is hard to predict. You know, predictions are always hard, especially if they're for the future. But what we can do is we can look back and ask ourselves, is there any other case like this that now we know, it used to be very abstract 100 years ago, but now makes a big difference? And in this particular context, the best example is the GPS constellation, something that you use on your phone when you want to find your way around the world. It does not work, the calculations do not work unless you use Einstein's theory of general relativity. So back when Einstein did it, nobody could ever predict that his abstract theory will help us today, navigate the world, and yet it does. So maybe 50 years from now, 100 years from now, what we learn will be, in a way, technologically important.
Thank you.
Thank you.
Sorry.
Yeah, in such a big effort, I was wondering, are you having any error correction or software adjustments to your data that maybe you didn't anticipate, which is maybe causing it to take longer to come out, or is it the data coming in like you thought?
Sarah, would you like to? Oh, Shep, did you want to press?
Yeah, so the instrumental effort is tremendous for this. We're taking telescopes that were not normally meant to do this kind of work, and we're refashioning them, so we're making an entirely new instrument. And one of the key things that it's what we call a heterogeneous array. Every telescope is different. So when we took our first data in April 2017, we really had to look at the response matrix. We had to see what the data looked like as it came through. So we've spent the last 2 years being very, very careful and understanding all of the instrumental effects. We think we have them all nailed down now. And I'm confident that this year will be our year.
Speaking of telescope arrays, was any thought given to using the Hubble or perhaps a lunar-based telescope to help in this effort? And how would that change the photo?
Sarah?
Well, so Hubble's operating at a different frequency, but we actually can combine it. As mentioning, we try to actually combine this with multi-wavelengths. So, in fact, we're not just using Hubble, but we're using most of the NASA ground facilities and also some of the ESA ones to boot. And what was the second question? Sorry.
How would that change our photograph of the black hole by using something like that?
So it's not going, basically, there's only one instrument which can photograph a black hole, and that's the one that we've been trying to develop in terms of a direct image. But understanding the physics and how to interpret that, it actually is a very complicated process. And in fact, a lot of it comes down to particle physics and trying to understand the actions of these individual particles and their distributions. And those particles tend to emit light in many other frequencies. So what happens is, if, for instance, we combine our image, which gives us a sense of a lot of the physics and the scales, it's sort of one set of conditions that we need for our models. But then we have to look at these other telescopes and the data that they give us, particularly about the light-emitting particles. It's a new constraint, and together we can start to really constrain, especially the physics of what's happening around the black hole, not just the black hole itself. Yeah.
I guess I'm worried that I'll sound stupid asking this, so I just have to put that out there. I was really intrigued by the imagery of the plasma jets shooting out of the black hole, because I don't know what's going on in the black hole to matter that enters the event horizon. And it seems like what was presented is that matter starts to form a torus around it and gets converted directly into a magnetic field, and that's what causes plasma to be shot back out. So does matter stay matter? Or is there a conversion that's going on that was unclear on the slides, and I don't research these things?
It's not entirely clear to us either. That's the problem. There's quite a few different competing theories about this. But actually, the general idea is that we know magnetic fields are the only thing strong enough to confine. It's very similar to nuclear fusion, to confine this very hot plasma. So what we think is happening is that in the material that's falling onto the black hole, magnetic fields are generated, similar to a dynamo, like in our sun or the core of the Earth. These field lines get pulled in and pressed up against basically the black hole, which is rotating very quickly, and then they sort of spiral outwards. And the material inside, that's something we're still trying to understand. It could be material that almost gets created from the strong magnetic fields, or it's dragged up along from the disk, and maybe a bit of both.
Thank you.
So just to be clear, material is not coming out from the black hole. It's swirling around the black hole and is pulled up. If you picture a spring coming out of the poles, that what Sarah was showing you was how that material swirling around gets pulled up magnetically through the spring, so to speak.
But that being said, the magnetic fields are possibly tapping the spin energy and getting a bonus from the black hole. Yeah.
So in Interstellar, Christopher Nolan and Kip Thorne tried to imagine what types of things this might look like. Do you think they got things right or wrong? Do you love it? Do you hate it? What are your thoughts on that?
This is a very nice question. I have two answers to it. One is Kip Thorne is the father of this field. So we all learned, everything that we know about general relativity and how to apply it, reading his books and reading his papers. Now, Kip Thorne did write the correct equations, and he did help them develop the correct computational methods to do it. But talking to the filmographer, they realized that when they made the pictures that look like ours, they did not like it. So they actually started removing physics and started making it more visually, pleasant to the eye. So yes, in principle, their calculation is correct. In practice, it's more visually pleasant, a poetic license to do it. The one thing that I would add is the thing that we take special pride of. If you look at the Wired magazine review about what they have done, they say that it takes them hundreds of hours on supercomputers to render a single picture. And I think you can see, as we say, that we can actually do it faster just waving our hands. So we're very proud of, having a chip that compared to Hollywood.
Nice.
Yeah, I'd like to add one thing about that. Dimitrios explained that very nicely. The other thing is to understand that when we do science, we're doing it for science's sake, right? We're not doing it to make a movie necessarily, or for the quarterly bottom line, or for the news cycle. Some of these scientific questions take long periods of time and investment to really pay off. So the GPS that Dimitrios talked about, it took 100 years really to come to fruition. And to do that, you need backing. You need people who believe in you. And we're very fortunate to have foundations like the National Science Foundation, foundations in Europe, private foundations, who are willing to take the long view, because we need to build a team. There's 4 of us here, there's 200 around the globe. You need a global team to build a global telescope. And it's only if you take the long view and you get the support you need that you can accomplish these kinds of things.
We have had a few breaks. One break that that comes to mind is that we need a telescope the size of the Earth, and we happen to have a planet of the right size. Another is that the frequency, that the wavelength of about 1 millimeter that gets you through the junk in our atmosphere and in space is also the peak of what's emitted from close to the peak of what's emitted from around the black hole. And for the first time, we have the ability to process this amount of information, petabytes of data, which is, kind of part of Moore's law. So, I mean, it's taken, if you ask, sometimes we want to know, why does something happen roughly when it happens? It's taken a lot that has had to come together theoretically, computationally, electronically, observationally. All of these things, it's a huge amount of work for all these hundreds of people.
Yeah.
Thank you for the presentation. My question is, what benefits, if any, do you anticipate your project bringing to the understanding of dark matter?
So this is a very deep question. One of the things that's interesting is that people think that when galaxies are formed, I was showing these mergers, basically the gravity in these systems is being dominated by predominantly this matter that we can't actually see. And so when the black holes are forming in the centers of the galaxies, we think that this is related to the process of dark matter also converging to the centers, where the gravity, like the core of our Earth is the heaviest place because of gravity, most compact. So the center of galaxies are predicted to have a kind of cusp of dark matter. And one of the things that we hope to be able to do is, by measuring a very precise mass within a very small distance, we can place in probably the strongest limits actually on the amount of dark matter in the systems that we're looking at, particularly the black hole in the center of our galaxy and a nearby galaxy. And that should, I don't know if you'd be able to ever rule out dark matter, but it might put some constraints on which cross-section they're looking for. It's kind of, there's a lot of models out there. Yeah.
Hi. So I've done like a lot of reading about this, and I'm just curious. So I noticed with the black hole, like the Doppler shift causes like one side to be lighter than the other side. How exactly does the motion of like the gases like cause this to happen?
Do you mind repeating your last sentence, because I couldn't hear?
Why does the gas produce a Doppler shift?
Oh, I see. Okay, I can respond to that, yes. So the gas falls into the black hole and starts spinning really rapidly, rotating really rapidly. Just the usual example when you're on, in skates and you get your hands closer together, you start spinning rapidly and more rapidly. So everything around the black hole is moving at the speed of light around. And the part of light that is pointing towards you is Doppler shifted really highly towards you. The part that's pointing away from you in its rotation is Doppler shifted away from you. All the light from here is focused towards you. All the light from here is focused away from you. And this is what gives rise to that crescent shape that we find.
So it's sort of like the vector of
the vector
light.
is pointing towards you as away from you, correct?
So like if you were to like look at it from another perspective, it would be the same because a different vector would be pointing towards you. Okay.
Absolutely.
It's one of the interesting things that we see the shadow of the black hole, but anybody else in the universe, should they exist, would also see a shadow, right? So it's the light bending from behind the black hole. So we see one, vision that Einstein would see, and somebody else would see something else too. So everybody gets their shadow.
Okay. Yeah. Thank you.
I recognize the tremendous effort that goes into trying to put these signals together to get a single image. So let's talk about really big baselines. Does the James Webb Telescope at L2 help you? And is it possible to begin doing this kind of work on a really long baseline like that? It's about 1.5 million miles. And I guess leading in beyond that, could we put a telescope at L4 or L5? Is that even feasible with today's foreseeable technology?
Shep?
Yeah. I thought we were being ambitious, putting telescopes around the world. You want to go for galactic domination. I admire your moxie, young man. So the answer is, as Peter said, this is a Goldilocks problem. We have just the right size Earth with just the right wavelength of light to image this black hole at the center of our galaxy and also in another galaxy, M87. We could go into space, but the James Webb Telescope, as powerful as it is, does not look at the radio wavelengths that we would need. So all the telescopes really have to be observing the same wavelength in order to play this trick of a virtual mirror. That being said, we are thinking now about decreasing the wavelength of light, which would sharpen our resolution. And we're also thinking about going into space where the orbital time period for a satellite would sweep out so much UV coverage or so much baselines, or fill in the UV plane, or I'm using some jargon here, fill in the virtual mirror, that we could make movies instead of still pictures. Wow. So we're even thinking beyond these normal images. We want to make a movie in real time of things orbiting around the black hole. That's what we want to do over the next decade.
If I may add something to this, one of the biggest problems that Shep knows a lot about with this project is not that we have the telescopes that much far apart, but we collect so much data, about the petabytes of data every night of observing, that there's no way that we can transfer this data through the internet. So what we actually do is we take our hard drives and we FedEx them from place to place. This is much faster than any cable that you can ever find. And sometimes FedEx delivers fabric instead of hard drives. It actually happened to one of the computer centers, and we had to trace the hard drives, and clearly somebody got hard drives instead of fabric. But this is the big... it was not funny, right? So when it happened.
Well, actually, what we did was we made outfits out of the fabric, so it worked out very well.
Yeah, this is our uniforms. But what the problem with space is that yet there's no FedEx to space. I mean, Mr. Musk might change that, but until that happens, one of the big problems that we will have with space to resolve is how do we transfer these petabytes of data with telemetry, which is an unsolved problem right now.
Yeah. It's kind of remarkable. There's some things that are very new school about this project, some things are very old school about this project. When I was a graduate student, someone told me, you can't beat the bandwidth of a 747 loaded with hard disk drives. And that's true today, right? I mean, even when I pick up some of these hard drives that we use and I walk across the room, just the act of me walking across the room is faster than the fastest internet on the planet, right? So when you want to move data around, sometimes you need a jet.
And you have to wait for the South Pole to open. Right. So we have some data from the South Pole telescope, and there's no way to get in and out during winter. And so part of the delay in getting the data is we had to wait for the plane to get out.
So my question was that when you're doing like projects like this that span the globe, and that requires a lot of international cooperation from different facilities, do like political conflicts ever interfere with your work? And my other question is like, when you're doing like long-form scientific projects like this, how do you ensure that you have like stable funding throughout the entire project that could last like decades or something?
I think the first one was politics, was it?
Conflict.
A conflict. Well, I'll take the first part, and then maybe someone wants to take the second part. So in a very long baseline interferometry and science in general, we're really politically agnostic. We don't want to let politics interfere at all. And by the very nature of what we do, we cross borders, we cross boundaries, and we involve scientists all around the globe. We have telescopes in Chile, of course, in Europe. We have colleagues in Asia. And when we come together at our collaborative meetings, we discuss science. And that's the bottom line, and it really brings people together. So in my estimation, this is an enterprise that really just crosses borders, and we don't worry too much about that. So conflict has not been a problem so far.
I mean, one thing that happens is we need the cooperation of the weather gods when we're observing. We need all these stations all over the world, from Greenland, the South Pole, Spain, France, Arizona, Hawaii. All these places have to have good enough weather because here are these photons, and they've been working for tens of thousands or more years, millions of years to get to us, and then they can get eaten up by a cloud right before they land on our telescopes. So telescopes can freeze over, to get snow melt on them and then freeze. They can stop work. There are a million ways this cannot work. So everything has to work for those nights that we're observing for us to get the data we need.
Should we talk about the funding? Yeah, the second part.
Go ahead.
Wow.
Yeah,
the funding one is, of course, in the ideal world, you want to have blue sky science, research, and you want to be able to understand these things and not be limited by election cycles. But of course, the reality is that the political landscape changes, and we've had to deal with that in this collaboration because we are international, and there you do come into the complexity of borders because some of the funding comes from the National Science Foundation, some of this comes from, the Dutch Research Foundation or the German, we have a European Union. And you have to get all of these things to line up with competitive grants and get the money in at the right time. And then, of course, looking to the future, you'd like to have stable long-term funding, but that's not always possible. So I think all science moves a little bit one branch to the next and tries to keep things going, but you always have a bit of uncertainty. Yeah.
Hi, so for this project, it's got a lot of similarity with like you said, the previous micrographia and X-rays. Based off all that previous work on something similar, how do you think the effects of those sorts of projects is going to influence how this one affects the world? We're photographing a black hole. What do you think is going to happen next based off of that?
Well, I think that there is a similarity in the sense that the microscope, the telescope, the X-ray opened up new forms of images that then created the possibility for very long-term investigations. And I think that if this is successful, of course, we will celebrate all night long. But it would only be the beginning of what we would hope to do. Because if this could work, if we could begin to get images, if we could begin to figure out ways of using space to have more telescopes, to look at sharper wavelength, sharper images, to make movies, we can get close in and really understand the dynamics of what happens in space and time near the horizon. There's a huge amount, there's really a new field to explore. And that's ultimately what's so exciting about this. I mean, to get the image will be great, to open up a field would be greater.
Yes, is the dynamics of the physics around the black hole known sufficiently well to have an understanding of the time scale at which things are happening around it? So in essence, can we expect to have an image or a motion picture? The other thing is, given the response time of the instruments, can we have something similar to a blurry image because of how fast things are going on around the black hole?
Those are good questions, Demetrios.
Yeah. So this is actually a very good question, and whatever I will say assumes that Einstein was 100% right? Because we have to use the theory to make those calculations. So how fast things move around the black hole, according to Einstein, depends primarily on the mass. So for the supermassive black hole in the center of the other galaxy, the M87 galaxy, things move at time scale of days or months. So when we spend 6 or 8 hours looking at it, we're taking a snapshot. So that is a very simple, clean problem. The black hole in the center of our galaxy is 1,000 times smaller. So whatever is a day for M87 is a minute for us. So things move at time scales of minutes to hours. And there we need completely different tools to be able to deblur the picture. And we have developed a lot of those tools, both for the snapshot images, which are straightforward, and for the ones that need to be blurry.
I want to add, if I could, one thing to that. It's an excellent question. One thing we do is we also don't need to make images. So we don't want to put all of our eggs in one basket. And it turns out that using some of the raw data from the instruments that we use, we can make EKGs, if you will, or time chart recordings of signals from the boundary of the black hole. And there, if something's orbiting the black hole, we would see these spikes. And as Demetrios was saying, for the center of our galaxy, matter orbits around every half an hour. Imagine that. Matter orbiting around something like the orbit of Mercury, but in half of an hour. That's how fast things are moving around the black hole. And if we saw these blips and we were able to time them, we could put a clock around motion of this black hole, and that by itself is a separate test of Einstein.
Last question.
Hi. So I was wondering, does the effect of, does time dilation from the massive gravitation of the black hole have any effect on the data?
Yes. Everything that we've talked so far is timescales as measured by somebody on Earth. Things happen at a very different rate close to the black hole, and actually that rate changes substantially as you get closer and closer to the event horizon. Things slow down as you get closer, as far as we can tell, as things get closer to the black hole. Of course, for the plasma that is next to the black hole, nothing happens. This is the beauty of black holes. Time depends on where you measure it.
They're very strange objects. If you were to fall into a big black hole of the kind that we're interested in imaging, you fall past the horizon and not know that anything much had changed. But if we looked at you falling in, or you looked at me falling in past the horizon, you would see me get oranger and redder and slow down, and my heartbeat would slow down, and you would never see me cross the horizon. So they're strange and wonderful effects in black holes, and we hope to understand more of them soon. Thank you all for coming. Thank you, colleagues.
Thank you.